All right, so get ready, because today we are going deep into some math that'll really make you think.
Yeah, definitely some mind-bending stuff.
We're looking at Christine Gassner's paper, AC and the Independence of the Law of Trichotomy in Second-Order Henkin Logic.
Oh, a classic.
It's a tough one, but trust me, you're going to be surprised by what we find. We've got excerpts from the paper ready to go, all about choice axioms and what they mean in this really interesting system.
You're not kidding about interesting. This paper gets right to the bottom of some big questions in set theory, the role of choice and all that.
Right, exactly.
Most mathematicians, they're happy working with Zermelo-Fraenkel set theory, where the axiom of choice is king.
Makes sense.
But Gassner's work, it's in second-order Henkin logic, or HPL. And it really throws a curveball into things.
Yeah, it's like HPL doesn't follow the same playbook as standard set theory.
Not at all.
Instead of letting us just make any old set we want, it limits us to definable collections, sets that you can describe with a formula.
It's kind of like set theory, but with a more constructive feel to it.
Exactly.
Yeah.
So within this framework, Gassner dives into what happens when you have a specific set of choice axioms called the Ackermann axioms of choice.
Right, and in particular, the subset called HAC.
Gotcha.
These axioms, they're all about one-to-one correspondences between sets.
Okay.
Now, you might think that in a system where you define your sets so carefully, something like the law of trichotomy.
TR, right.
Yes, TR, which says any two sets are either smaller than, equal in size to, or larger than each other, you'd think that would just follow naturally from HAC.
Sounds reasonable.
But Gassner shows us that's not the case at all.
And that's where things get really cool, isn't it?
Absolutely.
She uses the power of model theory, these things called permutation models, pounds and compounds,
Powerful tools.
to show that TR is actually independent of HAC in HPL. Can you walk us through these models? How do they work, and why are they so important for the proof?
Sure. Permutation models. Think of them like building your own little mathematical universes. You get to tweak the rules and see how different axioms behave.
Interesting.
The key is that these models are built without using the axiom of choice at all, which is crucial to show independence.
Why is that?
Well, if you want to prove principle A doesn't automatically lead to principle B, you need to create a world where A is true, but B isn't.
So it's about finding those exceptions to the rule, right?
Exactly.
So pounds, the basic Fraenkel model, that's our starting point.
A kind of baseline universe.
What makes this model tick, and how does Gassner prove that choice 11(1)HH actually holds in this setting?
Well, pounds is built using the set of natural numbers as its individual domain.
Okay.
And the important thing here is that every predicate in the model, it's determined by a finite number of individuals. We call that its support.
Support?
And this idea of finite supports is essential for the entire proof. To prove choice, 11 or 1H holds in towns, which is about choosing unique individuals based on a formula H, Gassner uses a really clever construction.
Okay, break it down for us. Where do we even start with a proof like that?
Great. So first, we pick a formula, H, and its corresponding stabilizer.
Right.
This stabilizer, it's a finite subset of the natural numbers, and it captures the essence of how the formula behaves, in a way.
Okay, and then what?
Then, using the stabilizer, we partition the entire set of natural numbers into a finite number of sets.
Like dividing them up.
Exactly, a p-adequate partition. And individuals within the same set of this partition, they act similarly with respect to formula H.
All right, so we've divided up our universe based on this stabilizer and how it interacts with our chosen formula. What's next?
Next, we carefully choose one representative from each set in the partition. This collection becomes our choice set.
So it's like choosing a captain for each team.
Precisely.
Yeah.
And using this choice set, we define predicates in a way that respects the structure given by the stabilizer. This construction is pretty complex, but it lets us systematically choose predicates that fulfill the conditions of our choice axiom, choice 11(1)HH, which ultimately shows that it holds in 10 pounds.
That's clever. But I have a feeling this is just the tip of the iceberg. Things are about to get even trickier when we move to compounds, which is basically a bunch of these basic Fraenkel models combined, right?
You got it.
What's the reason for jumping to a more complex model like that?
Compounds, that's the stage where we can really demonstrate the independence of TR.
Oh, okay.
It allows us to use the structure of multiple copies of 10 pounds to show how TR can actually fail, even when HAC is true.
Okay, now I'm really intrigued.
It's pretty fascinating stuff.
Let's get into the specifics of compounds and see how this independence proof really works.
Buckle up. It's about to get really interesting.
Okay, so we've got these compound models. Like you said, each one is like a mini universe of natural numbers all bundled up together.
Right, a whole bunch of them.
I'm guessing the way these copies interact is what's key to breaking the law of trichotomy.
Exactly. Let's say we want to compare two of these copies inside compounds.
Right.
Call them I1 and I2. And we want to use trichotomy to compare them.
All right.
If TR was true, we should be able to find a one-to-one correspondence between them, right?
Yeah, that makes sense. So we're looking for a predicate, some kind of mathematical rule that links each element in I1 to a unique partner in I2.
That's the idea. But remember, in compound, every predicate needs a finite support.
Right. We talked about that before.
That means there's a finite set of individuals that totally determines how that predicate behaves.
Oh, I see.
Now, I1 and I2, they're infinite copies of the natural numbers.
So they go on forever.
Exactly. So we can always find elements in them that are outside of this finite support. Elements that the predicate, in a way, doesn't see.
It's like there are blind spots in the predicate's vision caused by the limitations of having finite support.
Precisely. And this is where the structure of compounds becomes really important.
Okay.
We can use these blind spots, these gaps, to our advantage with permutations.
Permutations, right? Those are like rearrangements of elements in a set.
Yep. And in cons, we can find a permutation that swaps two of these unsupported elements.
Like one from I1 and one from I2.
Exactly. But it leaves everything in the finite support fixed.
So we're swapping elements that the predicate isn't really paying attention to, but keeping the core structure, the part determined by the support, untouched.
That's it. And that's what messes up the whole one-to-one correspondence.
How so?
Well, after we do this sneaky swap, our carefully built predicate is forced to map an element in I1 to two different elements in I2.
Ah, that's not allowed in a one-to-one relationship.
Nope, not at all. So we've basically broken the trichotomy in compounds by taking advantage of those finite support limitations and these clever permutations.
I see. So we've shown that trichotomy doesn't always hold in compounds. But how does this specifically demonstrate that HAC doesn't imply TR?
Because here's the amazing part. Even though TR fails in compounds, Gassner's proof shows that HAC, those 1-1 Ackermann axioms, they still hold true.
Wait, so even though we can break trichotomy?
Even then. It's basically a generalization of the technique we used for towns. You know, carefully breaking down the domain based on stabilizers, constructing p-adequate partitions, and defining choice functions and predicates that work perfectly within the structure of compounds. It's all very precise and clever.
So even with multiple copies of 10 pounds all tangled up together, we can still meet all the requirements of HAC. But trichotomy, which seemed so straightforward, falls apart because of the unique structure of the model.
That's the beauty of it.
It really shows they are independent of each other.
And this result has some big implications for understanding choice principles in different logical systems.
Right, because it shows how closely linked truths are to the axioms we choose.
Exactly. It highlights that delicate balance. What seems obvious in one system, like the link between choice and trichotomy, might be totally wrong in another.
It's like math isn't just about following a set of rules, but about exploring what those rules actually lead to in different contexts.
And sometimes those consequences can be pretty surprising.
Absolutely. But before we wander off into the philosophical side of things too much, let's switch gears and talk about that interesting open question that Gassner brings up at the end of her paper.
Yeah, the one about TR1 and ZL1.
That's the one. She's looking into the relationship between TR1, trichotomy for unary predicates, and ZL1, Zorn's lemma, for unary predicates, all within HPL. What makes this question so important, and why is it still unanswered, even after all this deep analysis?
Well, this open question shows how math is always evolving. Even with these awesome tools like permutation models, some connections between basic principles remain a mystery.
Okay.
In this case, we know ZL1, which says you can always find a biggest element in certain ordered sets, implies TR1 in HPL.
That makes intuitive sense. If you can always find a top dog, comparing sizes becomes pretty easy.
Right. But the other way around, whether TR1 implies ZL1, that's still a big question mark.
So it's like looking at two sides of a coin, but not knowing for sure if they're actually connected. Could there be a model of HPL where we can compare sizes of sets with unary predicates, but Zorn's lemma fails, meaning we can't find those biggest elements?
That's the million-dollar question, and it highlights the subtle nature of choice principles in different axiomatic systems. It challenges us to think beyond simple implications and really dig into how these principles work together.
Yeah, it's easy to think, well, if we can compare sizes, we should definitely be able to find those maximal elements. But Gassner's work reminds us that intuition can be misleading in the world of formal systems.
For sure.
This open question really underlines the fact that even in areas of math we think we know well, there are still uncharted territories waiting to be explored. Math is an ongoing journey, full of unexpected twists and turns. Before we wrap up our deep dive, let's take a minute to think about the key takeaways for our listeners. What are the big aha moments you hopefully walk away with? What makes this exploration of HPL and choice axioms relevant to the broader mathematical world?
That's a great question. First of all, I hope this deep dive has shown everyone just how rich and nuanced the foundations of mathematics really are. Exploring different systems like HPL with its unique rules and limits helps us appreciate the wide range of logical possibilities out there.
It's like realizing the mathematical universe is far bigger and more amazing than we first imagined. But beyond expanding our horizons, are there any... So it's not just about blindly following the rules, but about understanding what those rules lead to and recognizing that those consequences might change if we even slightly adjust the rules.
Exactly.
It's a call for a more critical way of thinking about the assumptions we make in math. But beyond the technical stuff, I can't help but think there's a philosophical side to all this too. What do you think? Does exploring the abstract world of formal systems tell us anything about the human experience?
I think so, definitely. While this might seem abstract and far removed from everyday life, I believe it touches on big questions about freedom, determinism, and the limits of what we can know. If the idea of choice can lead to such unexpected outcomes in a formal setting, it makes you rethink your own choices and all the things that influence them.
Makes you wonder if there are hidden links between these abstract principles and how the universe itself works. Perhaps the limits of choice we see in HPL are reflections of some deeper truth about reality.
Makes you think, doesn't it? Even in pure logic, we find mysteries we can't solve, principles that go against our gut feelings.
It's humbling, for sure.
Maybe these limitations on choice we see in HPL, even that unresolved link between TR1 and ZL1, they're not just mathematical quirks. Maybe they reflect deeper truths about how things really are.
Like the universe is working with a set of rules we're only starting to understand. And who knows what other surprises are out there just waiting to be found. This deep dive has definitely opened my eyes to how vast and complex math really is.
It's a journey that never ends, full of unexpected turns and amazing views. The beauty of math isn't just about getting the answers, but about the exploration itself, that constant push to understand, to question, and refine what we think we know.
And that pure joy of finding ideas that challenge us and make us expand our thinking, it reminds us that learning isn't passive. It's about actively engaging with the mysteries of the universe.
I like that. Well said. And even though we may never fully solve all those mysteries, the journey is a reward in itself.
Well, on that note, I think it's time to wrap up this deep dive into the fascinating world of second-order Henkin logic. We started with familiar territory, choice axioms, then went into uncharted waters with permutation models. And we found some surprising truths about how independent fundamental principles can be. We wrestled with complex proofs, thought about unanswered questions, and even glimpsed the philosophical side of these abstract investigations.
It's been quite the intellectual adventure, that's for sure.
Absolutely. And I hope everyone listening has come away with a new appreciation for how powerful and beautiful math can be.
I hope so too.
Thanks for joining us on this journey, and until next time, keep exploring, keep asking those questions, and keep diving deep into the wonders of mathematics. All right, welcome back everyone for another deep dive.
Glad to be here.
This time we're really going deep.
Deep into the math.
Second-order logic's on the menu today, specifically the independence of axioms within that framework.
We're going to be untangling some seriously abstract concepts.
Buckle up. Luckily, we have a true expert in logic with us today.
Oh, stop it. You're making me blush. I'm happy to help guide us through.
So this paper, the one we're diving into, is called AC and the Independence of the Law of Trichotomy in Second-Order Henkin Logic.
A real mouthful, I know.
I know our listeners are pretty familiar with second-order logic already.
Oh yeah, they're a sharp bunch.
But could you remind us quickly why it's the right tool for this kind of exploration?
Absolutely. Second-order logic, well, it lets us quantify over sets of objects. It's not just about individual objects like we see in first-order logic.
So instead of saying there exists an X, we can say there exists a set of X's.
Precisely. And that's crucial for expressing those ideas for all subsets of a domain, you know?
Ah, right. Because then we're talking about choice and order. And those involve sets, not just single things.
Exactly. You got it.
Now, on to Henkin interpretation.
Uh-oh, here comes the tricky stuff.
I remember it being a bit more flexible compared to the standard interpretations.
You're right, it is a bit more relaxed. With Henkin, not every single subset of a domain has to be considered.
It's not as strict.
Not as strict, yeah. And that's really important when we want to show that certain axioms are independent from others.
So we have more room to play around and see what happens when some axioms are true and others aren't.
Exactly. It opens up a whole world of possibilities.
I see. So let's move on to the main players here. The Ackermann axioms of choice, or HAC.
Ah, yes, HAC.
What makes them so special, and why is this paper so focused on them?
Well, HAC is all about expressing choice, but in the language of second-order logic. Specifically, it uses one-to-one correspondences between sets.
One-to-one, like matching each element in one set to a unique element in another.
Precisely. And what this paper does, the really cool part, is it proves that HAC is consistent with the basic Fraenkel model of second-order logic.
Consistent meaning they don't clash.
Right. No contradictions.
Okay, but I gotta ask, why is that consistency so important?
Well, the Fraenkel model, it's like a cornerstone of set theory, a really fundamental model. So proving that HAC plays nicely with it is a big deal.
So it's like ensuring that a new piece of software works perfectly with your operating system.
A perfect analogy. It means that HAC doesn't break anything within this crucial framework. It strengthens our understanding of both HAC and the Fraenkel model.
Gotcha. So to get to these results, the paper uses some pretty heavy-duty math tools.
Yeah, we're going full mathematician here.
Permutation models and finite stabilizers are the big ones, right?
Those are our weapons of choice today.
Can you give us a quick rundown of what those tools are and how they help tackle this problem before we dive into the specifics, of course?
Of course. Think of permutation models, like shuffling a deck of cards. We can rearrange the elements of a model in very specific ways.
So we're mixing things up.
Exactly. And by doing that, we can see what properties stay true even when we shuffle things around.
Interesting. And where do the finite stabilizers come in?
Well, finite stabilizers help us break down these complex shuffles, these permutations, into smaller, more manageable pieces.
So it's like grouping some cards together before shuffling so we can see what happens to those specific groups.
Perfect analogy. That's exactly what we're doing.
All right, I think I'm starting to get a feel for the tools we're using. Now let's get into the nitty-gritty. The paper tackles the proof that the basic Fraenkel model satisfies choice 1HH.
That's a key axiom within HAC.
Right, so how do they go about proving that? Where do our fancy permutation models and finite stabilizers come into play?
Okay, so they start by assuming the antecedent of the 1-1 Ackermann axiom, which basically means they're saying, let's assume the specific condition holds true in the basic Fraenkel model.
And see if it leads to the conclusion the axiom states.
Exactly. Now, to reach that conclusion, and that involves finding the right choice function, they use something called a p-adequate partition.
P-adequate partition?
Mm-hmm.
That sounds a bit intimidating.
It's really not that bad. They're just partitioning or dividing the domain of individuals into smaller sets.
Individuals?
Yeah.
Like specific numbers?
In this case, yes, natural numbers.
Okay, so they're dividing all the natural numbers into these smaller sets.
Right. And each of these smaller sets has a specific finite stabilizer, which we call P.
So they're breaking down this big problem into smaller, easier to handle chunks.
You got it.
And they use those smaller sets to define the choice function.
Yes. Step by step.
Smart.
And from each of these small sets, they carefully pick out representative elements.
Representatives.
Yeah.
Like delegates from each set.
You could say that. And these representatives are crucial for building that choice function we're looking for.
So they have these smaller sets. They've chosen their representatives.
Yeah.
What's the next step in building the choice function?
Well, this is where it gets a bit technical, but they define a choice function on this finite set of representatives. It's like they're building a smaller version first.
Okay, a model choice function. Makes sense.
Then, using this mini choice function and the properties of permutation models, they manage to construct a new predicate.
A predicate, like a statement that can be true or false.
Yes, exactly. And this new predicate is a part of the model, meaning it's well defined within the basic Fraenkel model.
So this predicate is how they satisfy the conclusion of the axiom.
You got it. And not just that, they show that this new predicate actually acts like a choice function.
Wow, so they've used all these tools and concepts to create something that perfectly fits what the axiom needs. That's some impressive mathematical maneuvering.
It really is. And they use a similar approach to prove that HAC also holds in a more complex model. the finite union of Fraenkel models, denoted by polens.
So they take this same strategy, adapt it, and show that it still works in a more complicated setting.
Exactly. It highlights just how robust and applicable HAC is. It's not just a fluke, it's a fundamental property that holds up even in these more complex structures.
That's pretty cool. We've covered so much ground already. Second-order logic, Henkin interpretation, the details of HAC, and even how permutation models and finite stabilizers play their part in these proofs. But there's still more to uncover.
Oh, we're just getting started. We haven't even gotten to the law of trichotomy or that open question about Zorn's lemma.
So much to explore, but we'll have to save that for next time. Join us for part 2 of our deep dive as we unravel the complexities of choice and order even further.
It's going to be a wild ride. Welcome back, everyone. Ready for round 2.
Let's do it. We left off talking about HAC and how it behaves in the Fraenkel model. Now it's time to tackle the other big concept in the paper. The law of trichotomy, or as they call it, TR.
Ah, TR. The idea that for any two things, one must be greater than, less than, or equal to the other seems simple, right?
Simple on the surface, but I have a feeling it gets more complicated when we're dealing with second-order logic and sets. And that's where TRN comes in.
You got it. TRN, that's our way of expressing the law of trichotomy in a way that applies to relationships between sets, not just single numbers.
So instead of just comparing two numbers, we're comparing these complex mathematical objects.
Exactly. It's all about n-ary predicates, relationships that involve multiple sets.
Okay, so we've got HAC representing choice and TRN representing trichotomy. And the paper goes to great lengths to prove that these two are independent in second-order logic with Henkin interpretation. What does that mean exactly?
In simple terms, it means that knowing one of these principles holds true doesn't tell us anything about whether the other one does.
So they're not inherently linked. That's kind of mind-blowing. Both choice and order seem so fundamental to math, I just assumed they'd be connected somehow.
Yeah, it's like finding out that two pillars holding up a building aren't actually connected, but the building's still standing.
That's a great analogy. But how do they actually prove this independence? Do those permutation models we talked about earlier come into play here?
They sure do. Remember, permutation models are like shuffling a deck of cards, letting us rearrange the elements of a model and see what properties stay true.
So they're creating these mathematical worlds where one concept holds, but the other doesn't.
You got it.
Yeah.
It's like running simulations to test out these ideas.
Okay, so by building these specific models, they show that HAC and TRN can exist independently. That's pretty clever.
It is, and it highlights just how complex and nuanced second-order logic can be. Things aren't always as straightforward as we might think.
So how do they actually go about building these models where one concept holds and the other doesn't? Is it the finite stabilizers again?
Finite stabilizers are definitely involved, but the strategy is a bit different here. They've already shown that the basic Fraenkel model satisfies HAC, right? Now they need to show that you can have a model where HAC is true, but TRN is false. And they do that by taking that basic Fraenkel model and building on it, creating something they call compounds.
Compounds, a finite union of Fraenkel models. Sounds complicated.
It is a bit more intricate, but the basic idea is that they're expanding the model where HAC works to create a new one where TRN fails.
Okay, like taking a working engine and adding some new components to see how it behaves under different conditions.
A perfect analogy. And when they analyze this new compound model, they find that, yep, it satisfies HAC, but doesn't satisfy TRN. Boom, independence proven.
That's so cool. It really shows the power of these mathematical tools, how they let us construct these intricate models and really explore the nuances of these concepts.
I know, it's amazing what we can do when we go beyond intuition and start using these powerful techniques. And speaking of pushing boundaries, just when you think they've wrapped things up, they throw a curveball. Zorn's lemma.
Oh yeah, the cliffhanger from last time. Can you remind us what Zorn's lemma is all about and how it connects to HAC and TRN?
Zorn's lemma, or ZL for short, is like a superpower in set theory. It lets us prove that certain mathematical objects exist without having to actually construct them.
It's like knowing the answer to a puzzle without knowing how to solve it.
Exactly. And the interesting thing is, in second-order logic with Henkin interpretation, ZL is actually equivalent to the full axiom of choice.
Wait, so ZL brings in the full power of choice, but didn't we just establish that choice and trichotomy can be independent?
That's what makes this so fascinating. The authors leave us with a big open question. Can Zorn's lemma be derived from the law of trichotomy in this framework?
So even though HAC and TRN are independent, there's a chance that this stronger form of choice embodied in ZL might actually be connected to TRN. It's like those two branches of a family tree that seem separate but might actually share a common ancestor further back.
That's a great way to think about it. And it leaves us with so much to ponder. Is there a hidden connection between choice and trichotomy that we haven't uncovered yet? It's a question that could lead to some really groundbreaking discoveries.
Welcome back to our deep dive, everyone. I hope you're ready for the final stretch.
You know I'm ready. We've journeyed into the depths of second-order logic, explored the mysteries of HAC and TRN, and even pondered the implications of Zorn's lemma. What a ride.
It has been quite a journey. And as we wrap things up, I want to highlight a couple of smaller details from the paper that really stood out to me.
Oh, I love the little details. They often hold the most interesting insights.
Right. One thing that caught my attention was their discussion of the meta-theory they used for the proofs.
The meta-theory, you mean the underlying logic they use to prove their points?
Exactly. They emphasize that they didn't need the full power of Zermelo-Fraenkel set theory with the axiom of choice, ZFC, to get their results. Now that you mention it, I do remember them touching upon that. But why is that significant? Doesn't it make their findings less valid if they're using a weaker system?
Not at all. Actually, it strengthens their argument. By showing they can prove these results about choice, or the independence of certain axioms from choice, without relying on the full axiom of choice in their framework, they're demonstrating a certain level of self-sufficiency.
So it's like they're saying, look, we can explore the nuances of choice without taking the strongest version of choice for granted.
Precisely. And this minimal reliance on the full axiom of choice opens up exciting possibilities. Maybe these results about choice hold true in even weaker foundational systems.
It makes you wonder what else we might discover if we start questioning those foundational assumptions, right?
Absolutely. And speaking of extending these findings, the authors also suggest that their techniques, while focused on HAC specifically, could be generalized to encompass all Ackermann axioms of choice.
So their findings might have implications beyond the specific case they investigated.
Exactly. It hints at a broader applicability of their methods and conclusions. This work might give us a deeper understanding of how choice interacts with other mathematical principles in a more general sense, like we're just scratching the surface here.
This paper has been a real eye-opener. It's incredible how something so abstract can have such profound implications for our understanding of math and logical reasoning. It really makes you appreciate the power of these theoretical explorations.
It does. This paper beautifully illustrates how mathematics is always evolving, with different ideas intertwining to create this incredibly rich and complex tapestry of knowledge.
Well said. This deep dive has certainly expanded my mind. We've waded through the intricacies of second-order logic, wrestled with the complexities of choice and trichotomy, and glimpsed the potential connections to Zorn's lemma and the full power of the axiom of choice.
We've covered a lot of ground, that's for sure. And while we may not have all the answers, I think we can all agree that this exploration has deepened our appreciation for the beauty, complexity, and interconnectedness of mathematical ideas.
Absolutely. And who knows what new discoveries await us as mathematicians continue to grapple with these fascinating questions. To all our listeners, keep those minds curious, keep exploring. There's a whole universe of mathematical wonders out there waiting to be discovered. Until next time.
Goodbye, everyone.
Welcome back to the Deep Dive. Ready for a real brain workout today?
Always up for a challenge.
Awesome. We're diving into some pretty hardcore math this time.
Oh, laid on me.
Second-order Henkin logic. Specifically, this 2024 paper by Christine Gassner, AC, and the independence of the law of trichotomy in second-order Henkin logic. A fascinating read, really gets you thinking.
Yeah, Henkin logic always throws some curveballs.
No kidding. But before we go full-on math nerd, maybe a quick recap for anyone who needs it. What makes Henkin logic stand out from, say, regular set theory?
Right, so in a nutshell, Henkin logic, it's not about the sets themselves, like who belongs where.
More about how the logic plays out within specific structures, right?
Exactly. Imagine like mini mathematical universes, each with its own rules, its own objects.
So Henkin logic looks at what happens to our logical statements when they're confined to these universes.
Precisely.
Okay, cool. So now Gassner adds these things called the 1-1 Ackermann axioms of choice, HAC for short. These aren't your average everyday choice principles, are they?
Definitely not. Way stronger than what we usually see in Henkin logic. And with stronger axioms come?
More interesting consequences.
She could say that.
I mean, even the basic axiom of choice gives us some crazy stuff, like the Banach-Tarski paradox. Do these HAC axioms lead to similar weirdness in Henkin logic?
Oh, absolutely. But here's the thing. A lot of the tools we use in normal set theory, they don't work so well in Henkin logic.
So figuring out what these pumped-up choice axioms do in Henkin logic, it's like exploring uncharted territory.
You got it.
Okay, I'm intrigued. Now, Gassner uses this thing called the basic Fraenkel model to really put these axioms through their paces. What's so special about this model? Why use that one?
It's like a purpose-built testing ground for logic. Instead of sets, we've got individuals, predicates, and permutations. Think of it like a very customizable Lego set.
Okay, I'm kind of with you. So we have the individual pieces, rules for how they fit together, and then we can shuffle them around.
Exactly. This gives Gassner a lot of control over the environment to see how the HAC axioms behave.
So what happens when we unleash the HAC axioms in this Fraenkel model? Do they play nice?
Actually, yeah, surprisingly they do. Gassner proves that the 1-1 Ackermann axioms hold true in this model.
Okay, that's unexpected.
But here's the twist. The well-ordering principle, which usually follows from the axiom of choice in regular set theory.
It doesn't hold in the basic Fraenkel model.
Yup.
Whoa, wait. That means you could have a set where you can pick an element from any subset, but you can't put the whole set in order.
Exactly.
That's mind-blowing. Really shows the difference between Henkin logic and standard set theory, huh?
Big time.
Yeah.
In Henkin logic, even these strong 1-1 Ackermann axioms, they don't automatically mean you have a well-ordered universe.
Okay, my head is spinning a bit. And this is just the basic model. I can only imagine what happens when Gassner kicks things up a notch.
Oh, you have no idea. We haven't even gotten to the permutation models yet. That's where Gassner combines multiple Fraenkel models and things get really wild, especially when it comes to the law of trichotomy.
Permutation models. Combining multiple models is like a mathematical multiverse. And that's where the law of trichotomy comes in. I'm definitely ready to hear more about that in the next part of our deep dive.
Okay, so we're stepping it up now. Permutation models.
Yeah, you mentioned these before. Combining those Fraenkel models,
Right.
it's like connecting our Lego universes.
Precisely. And what Gassner shows is when you build these permutation models carefully, you can actually create a situation where the law of trichotomy breaks down.
Whoa, hold on. The law of trichotomy, that's like a basic rule of sets, right?
Yeah, you'd think so. It says for any two sets, one can be injected into the other. Basically, you can always compare their sizes.
Seems pretty fundamental. How could it not hold up in these models?
Well, remember, we're in Henkin logic land now. Things work differently here. Gassner proves that even if the 1-1 Ackermann axioms are true, the law of trichotomy doesn't automatically follow.
No way. It's like finding a crack in the foundation of set theory. So how does Gassner prove this? Spill the mathematical secrets.
It's a pretty intricate proof. But one key idea is using those finite stabilizers we talked about earlier.
Vaguely rings a bell. Remind me about those again.
Right. So imagine you're shuffling the elements of our model around, right? A finite stabilizer for an element means only a finite number of shuffles will leave that element in the same spot.
Okay, so it's about which shuffles don't move certain pieces.
Exactly. And Gassner uses these stabilizers to partition the domain of the model, like dividing it into special regions based on how the elements are affected by the shuffling.
So we're slicing up our Lego universes strategically, but how does that help break the law of trichotomy?
This is the really clever part. By looking at how the permutations act on these partitions, and by building some very specific predicates, Gassner shows that the kind of mapping you need for the law of trichotomy, an injective mapping, it just can't exist.
Wow. So by messing with the partitions, controlling how elements can be mapped, Gassner forces the law of trichotomy to fail, even though those 1-1 Ackermann axioms are still in play.
Exactly.
That's some serious mathematical judo right there.
And it highlights a key takeaway. The law of trichotomy isn't some absolute truth in Henkin logic. It depends on the axioms you choose, the structure you're working with.
So even something that basic can change when you switch logical systems. That's pretty wild.
It is. It's like Henkin logic has this whole hidden world where the rules we're used to from set theory don't always apply.
Gassner's work is really eye-opening. Shows us how different these two systems can be.
Definitely. And there's still more to uncover. Remember that question Gassner leaves us with at the end of the paper?
Oh yeah, the one about Zorn's lemma. It's a whole other can of worms, right?
Big time. Does the law of trichotomy, even weakened, imply Zorn's lemma in Henkin logic? That's what we'll tackle in the final part of our deep dive.
All right, so we've seen the basic Fraenkel model. watched the law of trichotomy break down in those permutation models, and now we're left with this big question mark hanging over Zorn's lemma. Gotta admit, Zorn's lemma always kind of intimidated me.
Yeah, it's a powerful one, that's for sure.
Okay, so just to recap for anyone who needs it, Zorn's lemma, it's about partially ordered sets.
Right. It says, if every chain in the set has an upper bound, then the set itself has a maximal element.
Okay, even for a math nerd like me, that's a lot to unpack. Partially ordered sets, chains.
Yeah, let's break it down. So a partially ordered set, it's like you have a way to compare some of the elements, not necessarily all of them.
Like a hierarchy where we know A is above B, B is above C, but maybe we don't know how A and D relate.
Exactly. And a chain is a subset where everything is comparable, like a straight line going up that hierarchy.
Okay, so Zorn's lemma is saying, if every one of those chains has a ceiling, a top element within the set, then the whole set has a peak, a maximal element.
Exactly.
Got it. And we know in regular set theory, Zorn's lemma is pretty tight with the axiom of choice. But in Henkin logic...
That's the question, isn't it? Gassner's already shown us things don't always translate neatly between these systems.
Right. So whether the law of trichotomy, even a weaker version, whether that implies Zorn's lemma in Henkin logic, it's not a slam dunk.
Not at all.
It's amazing how this paper has opened up so many new questions. Like, we peeked into Henkin logic and suddenly all these familiar rules from set theory, they're wobbly.
Yeah, it really challenges those assumptions. What's true can change when you change the logic system.
It makes you realize how much there still is to explore in math.
Definitely.
Well, I'm super glad we took this deep dive. Started with choice principles, ended up questioning the very nature of order and comparison.
That's the best kind of deep dive, right? The kind that leaves you with more questions than answers.
Absolutely. And if you're listening and feeling inspired, I highly recommend checking out Gassner's paper yourself. Don't be scared by the fancy math. Just let your curiosity lead the way. You might be the one to figure out the connection between the law of trichotomy and Zorn's lemma in Henkin logic. Who knows?
And that's what we're all about here on The Deep Dive. Exploring, questioning, pushing those intellectual boundaries. So until next time, keep those minds curious, keep diving deep, and we'll see you in the next episode.
All right. Welcome back, everyone, to another deep dive.
Oh, yeah.
Today, we're going to be diving into the world of second-order Henkin logic.
Sounds fun.
And specifically looking at Christine Gassner's paper,
Okay.
which is titled AC and the Independence of the Law of Trichotomy in Second-Order Henkin Logic.
Nice.
Now, I know you, the listener, are already a math aficionado.
Right.
You probably follow this stuff pretty closely.
Of course.
But hopefully today we can dive into some of the more nuanced elements
Yeah.
and look at some of the surprising implications of
For sure.
some of these results.
Absolutely.
So as we go through this paper, let's kind of keep in mind this question.
All right.
How do these subtle shifts in logic
Yeah.
really impact our ability to prove mathematical truths?
Yeah, that's a really great question.
Like, imagine you're trying to organize an infinite library of books,
Oh, wow.
and you need a rule, an axiom to decide which book goes where.
Okay. Yeah.
But what if the usual rules don't quite apply?
I see. Yeah.
That's kind of what we're going to be looking at.
Interesting.
So right off the bat, Gassner kind of throws us a curveball.
Okay.
She says this in the paper.
All right.
This prompted us to examine the known proofs in more detail and to look for counterexamples. And that's the kind of statement that I think gets any mathematician's attention.
Yeah, for sure.
Because it's suggesting that some proofs that we might take for granted
Right.
that are perfectly valid in traditional set theory might completely crumble in the world of Henkin logic.
Oh, wow. Okay.
So for instance, she looks at the law of trichotomy, which states that for any two sets, one is bigger, smaller, or they're equal.
Okay.
And that's something that we kind of just take as a given in standard set theory.
Yeah, for sure.
But Gassner shows that it's not always guaranteed in second-order Henkin logic.
Interesting.
And that's kind of what we're going to be looking at today.
Okay, fascinating.
So one of the first things she dives into is this set called HAC, which stands for the 1-1 Ackermann axioms of choice.
Gotcha.
And she formally defines it as HAC equals DF, and then in brackets,
Okay.
choice 1, ochre 1, superscript H, open parenthesis H, close parenthesis.
Okay.
Such that H is a formula in L, open parenthesis 2, close parenthesis XD.
Right. Yeah.
Now, I know our listener, you're fluent in mathematical notation.
Oh, yeah, of course.
But for the sake of clarity, can you kind of unpack what's going on in that definition?
Absolutely. So we have that choice, 11(1) superscript H open parenthesis, H close parenthesis.
Yeah.
That represents a particular type of choice axiom.
Oh.
Think of it as a rule for picking an element from a set.
Yeah.
But it's specifically tailored to the logical situation described by this H.
I see.
So H here stands for any well-formed formula in second-order logic,
Well,
and it has variables x and d.
gotcha.
So, it's constrained by L open parenthesis 2, close parenthesis x, d.
Okay, so HAC is kind of like this toolbox filled with all these different choice axioms,
Right.
each designed for a specific logical task.
Yeah,
exactly.
And then Gassner explores whether these HAC axioms
Okay.
hold up in a particular model called the basic Fraenkel model,
Right.
which is denoted by the capital Greek letter sigma superscript 0.
Okay.
So why this model? What's so special about sigma superscript 0?
Well, this model is built on the idea of finite stabilizers.
Okay.
So imagine you have a set.
Mhm.
You can rearrange the elements,
Okay.
but you can only rearrange a finite number of them at a time.
Okay.
Now, a finite stabilizer for a given formula
Yeah.
is a finite set of elements
Uh-huh.
that once those are fixed, the truth value of the formula doesn't change,
Okay.
no matter how you rearrange the other elements.
So it's like having this limited set of controls
Yeah.
for how you can manipulate the set.
Exactly.
Okay.
Yeah.
And then Gassner dives into a proof
Right.
showing that HAC actually holds true within this model.
Okay.
So what's the key insight behind this proof? How does she actually show that? Well, the crux of the proof lies in the finite nature of these stabilizers.
Okay.
This finiteness allows us to apply choice functions
Uh-huh.
in a way that wouldn't be possible if we were dealing with infinite rearrangements.
I see.
Essentially because we can only move a finite number of pieces at a time.
Yeah.
We can ensure that our choices remain consistent even when we're dealing with infinite sets.
So this finite constraint
Yeah.
actually enables us to apply these really powerful choice axioms.
Exactly.
That's interesting.
Yeah.
And then Gassner uses some specific notation to express these ideas.
Okay.
Like the lowercase Greek letter alpha, subscript uppercase H, comma, uppercase P, space, lowercase Greek letter mu.
Right.
Can you give us a concrete example
Of course.
of what this represents within sigma superscript 0?
Absolutely. So let's imagine our infinite library again.
Okay.
This alpha, subscript uppercase I, comma, uppercase P, space, lowercase Greek letter mu,
Uh-huh.
refers to a specific book within that library.
Now, I represents the entire collection of books.
Gotcha.
P represents a particular arrangement of those books on the shelves,
Mm-hmm.
and pinpoints a specific shelf within that arrangement.
So it's like a really precise coordinate system
Exactly.
for locating a specific book within our infinite library,
Yeah,
even though the arrangement of the books might be changing according to these finite rules.
exactly.
And this notation allows Gassner to demonstrate how we can pick books,
Right.
how we can apply choice axioms in a way that respects the limitations of sigma superscript 0.
Precisely.
So it's fascinating how this model, which seems kind of limiting,
Mm-hmm.
doesn't actually restrict our ability to make these consistent choices.
Right. Yeah.
Now on page 4,
Right.
Gassner introduces a different model,
Right.
denoted by the italic lowercase k, and then the capital Greek letter sigma superscript 0.
Gotcha.
And she describes this as a permutation model.
Okay.
So what's the significance of bringing in this new model? Well, lowercase k, capital Greek letter sigma superscript 0
Yeah.
is like taking multiple copies of our infinite library,
Okay.
each with its own arrangement
Yeah.
and finite stabilizers,
Okay.
and then placing them side by side.
Right.
This allows us to compare and interact between these different libraries,
Yeah.
which opens up a whole new set of possibilities and challenges.
So we're kind of expanding our universe of books and rules.
Exactly.
That's really interesting.
Yeah.
And Gassner uses specific notation for lowercase k, capital Greek letters sigma superscript 0 as well,
Okay.
which she outlines in table 2.
Right.
What are some key things our listeners should keep in mind
Sure.
as we navigate this new notation?
So one crucial aspect is understanding how subsets are represented within lowercase k, capital Greek letter sigma superscript 0.
Okay.
She uses the notation lowercase Greek letter beta, open parenthesis, j, comma, I, close parenthesis,
Uh-huh.
where j tells us which copy of the library we're in,
Gotcha.
and I points to a specific subset within that copy. Okay.
Always respecting the finite stabilizers of that particular library.
So we're adding another dimension to our coordinate system.
Exactly.
We're not just locating books within one library anymore.
Yeah.
We're pinpointing them across these multiple interconnected libraries.
Precisely.
And it looks like Gassner uses this more complex setup to explore the limits of the law of trichotomy.
Okay.
And this is where things start to get really interesting.
All right.
But I think we should pause here for now.
Okay.
And let our listener kind of absorb everything.
Yeah, sounds good.
And we'll come back and pick up with the law of trichotomy in the next part.
Looking forward to it. All right. So we've laid the groundwork exploring HAC.
Yeah.
And how it functions within the basic Fraenkel model, sigma superscript 0.
Right.
But now let's turn our attention to compounds.
Okay.
This fascinating multi-library model that Gassner introduces on page 4.
Yeah, this is where things start to get really interesting.
It is. And as we navigate this new terrain,
it's important to remember that we're stepping outside the familiar bounds of standard set theory.
Okay.
And some surprising results await us.
Yeah, I'm particularly intrigued by how Gassner uses compounds to investigate the limits of the law of trichotomy, denoted PR.
Okay.
To refresh our memory.
Yeah.
Can you remind us what TR asserts in the general case?
Sure.
And then explain the specific notation Gassner uses.
Absolutely. So in simple terms, the law of trichotomy says that given any two sets, we can always determine if one is bigger, smaller, or if they're the same size.
All right.
Now, Gassner uses this notation, TR subscript n, which is defined as for all A, for all B, open bracket A dot B, close bracket, or open bracket B dot A, close bracket, close bracket.
Okay.
To apply this concept to sets defined by n-ary predicates.
Okay, I see.
Denoted A and B in her notation.
So A and B represent specific sets within our multi-library system.
Exactly.
What about the rest of that notation? What does all that mean?
So the symbol, open bracket, A dot B, close bracket, means there exists a one-to-one function from set A into set B. Essentially, it says we can map every element of A to a unique element of B. Potentially leaving some elements of B unmapped. And then the symbol, this kind of V-looking thing, represents the logical OR. So TR subscript n states that for any two sets, A and B, definable by n-ary predicates. Either we can map A into B, or we can map B into A.
So TR subscript n is a formal way of saying that we can compare the sizes of sets.
Exactly.
Even in this more complex world of compounds where we have these multiple libraries of sets interacting. Okay, cool. Now on page 5, Gassner constructs a specific example within compounds to demonstrate a very surprising result. Can you walk us through this construction?
Of course. So Gassner starts by carefully selecting elements from each copy of our library to create a set that she denotes as alpha subscript 0. Each element in alpha subscript 0 is chosen in a way that respects the finite stabilizers of the library it comes from. So think of it as forming a representative committee. Drawing one member from each branch of our multi-library system.
I like that analogy.
Yeah.
So alpha subscript 0 is like a snapshot of the diversity within compounds.
Exactly.
Capturing elements from each of its distinct libraries.
Precisely.
Okay, cool. And then on page 6, Gassner uses this alpha subscript 0 to define a choice function, which is denoted by the lowercase Greek letter phi subscript s.
Gotcha.
This function operates across all the libraries within compounds, kicking out elements in a consistent manner, guided by the structure of alpha subscript 0. It's like having a master librarian who understands the cataloging systems of each individual branch. And can select books accordingly.
Exactly. A very knowledgeable librarian.
Yes. So this choice function seems like a very powerful tool.
It is, yeah.
Does Gassner use it to prove something specific within compounds?
Yes. She uses phi subscript s to demonstrate that HAC, those specialized choice axioms we discussed earlier, hold true in compounds. This means that even in this more complex model with multiple interacting libraries, we can still make consistent choices from sets.
That's pretty remarkable.
It is, yeah.
So even though compounds is significantly more intricate than sigma superscript 0, it still allows for this coherent application of choice axioms.
Exactly.
But then Gassner drops a bombshell.
Okay.
She shows that even with HAC holding true, TR subscript 1 does not necessarily follow.
Hmm.
This seems very counterintuitive.
It is, yeah. It's a surprising result.
Can you elaborate on this a bit more?
Absolutely. So Gassner's proof,
Wait.
which is laid out in detail from pages 6 to 8, demonstrates that in compounds, the ability to make consistent choices using HAC does not automatically guarantee that we can compare the sizes of all sets.
I see.
Using TR subscript 1.
Okay.
Now remember, TR subscript 1
Right.
is the law of trichotomy applied to sets defined by unary predicates.
Okay.
So it's like saying that our master librarian, who can skillfully pick out books from each library branch, might encounter situations where they can't definitively say whether one branch has more books than another.
Okay.
Even though they can consistently choose books.
Yeah.
According to each branch's rules.
That's a great way to put it.
Yeah.
So this independence of TR subscript 1 from HAC is a pretty profound departure from standard set theory.
It is, yeah.
Where the axiom of choice generally implies the law of trichotomy.
Exactly.
Gassner's findings really highlight the subtle but crucial differences between these two logical systems.
Yeah, for sure.
This is a pretty significant moment in our deep talks.
It is.
It's clear that the world of second-order Henkin logic is full of unexpected twists and turns.
Definitely.
We can have a situation where these very carefully crafted choice axioms hold true.
Yeah.
Yet this seemingly fundamental ability to compare set sizes isn't actually guaranteed.
This isn't there, yeah.
And Gassner's careful construction of pounds and her very rigorous proof showcase the power of model theory.
Yes.
And really illuminating the nuances of these logical systems.
For sure.
I'm eager to explore where Gassner takes us next.
Me too.
It looks like on page 9, she starts to connect these findings to another well-known principle in set theory.
Okay.
Zorn's lemma.
Right.
Can you remind us what Zorn's lemma states and why it's relevant in this context?
So Zorn's lemma is this powerful tool in set theory.
Okay.
It essentially states that if you have a partially ordered set where every chain, a totally ordered subset, has an upper bound within the set, then the set must contain at least one maximal element.
Right. So it's a statement about the existence of maximal elements in certain types of sets.
Exactly.
Why is Gassner bringing this into the discussion now?
Well, both the axiom of choice and Zorn's lemma are often used to prove the existence of certain mathematical objects.
Okay.
And in standard set theory, they're actually equivalent. You can derive one from the other.
Okay.
Now, Gassner uses the notation ZL subscript n to denote Zorn's lemma applied to sets defined by n-ary predicates.
Okay, so in this context, ZL subscript 1 refers to Zorn's lemma applied to sets defined by unary predicates.
Exactly.
The same type of sets that we're considering with TR subscript 1.
Precisely, yeah.
Okay, so Gassner points out that while ZL subscript 1 can be derived from ACL1, which is a form of the axiom of choice, and second-order Henkin logic, it's known that both ACL1 and TR subscript 1 are independent of ZL subscript 1.
Interesting.
So we have this very intricate web of relationships here.
We do, yeah.
HAC holds in compounds. But TR subscript 1 doesn't necessarily follow. And ZL subscript 1, while derivable from AC11, is independent of both AC11 and TR subscript 1.
Yeah.
It's a lot to keep track of.
It is. It's pretty fascinating stuff, though.
It is, yeah.
Yeah.
And then on page 10, Gassner raises this fascinating question that emerges from this intricate web. Does TR subscript 1 actually imply ZL subscript 1 in second-order Henkin logic?
That's a great question.
And this seemingly simple question has really profound implications.
It does.
Because if TR subscript 1, this statement about comparing set sizes were to imply ZL subscript 1, a principle about the existence of maximal elements, it would reveal a deeper connection between these concepts in the world of Henkin logic than what we see in standard set theory.
Exactly.
It would be like discovering a hidden tunnel. Connecting two seemingly distant regions of our mathematical landscape.
Yeah, I like that.
So that's where Gassner leaves us, with this very tantalizing open question. It's an invitation to explore further. To delve deeper into the intricacies of second-order Henkin logic.
Absolutely.
And uncover its hidden truths.
I'm ready for part 3.
Me too. Let's take a break and come back.
Sounds good.
All right, welcome back.
Back again.
So we've been on quite a journey through this intricate world of second-order Henkin logic.
Absolutely.
And we've been guided by Christine Gassner's work.
Right.
And we've explored how choice axioms behave so differently in this realm compared to standard set theory.
For sure.
We encountered that surprising independence of the law of trichotomy, or TR1, from those one-to-one Ackermann axioms of choice, or HAC in the model compounds.
Okay.
And we even touched upon that intriguing relationship between TR1 and Zorn's lemma, ZL1.
Right, yeah.
So it's been an exploration filled with all these twists and turns.
For sure.
And these really profound insights.
Absolutely.
And as we go into the final section of Gassner's paper, we're going to encounter even more thought-provoking insights and open questions.
Sounds good.
So on page 11, Gassner shifts our attention to another model of second-order Henkin logic, which is denoted by a capital italic N.
Gotcha.
Can you tell us a bit about this model?
Sure. So N, as Gassner describes it,
Okay.
is a model where the domain of individuals is the set of natural numbers.
Okay.
And n-ary predicates are interpreted as subsets of n to the power of n.
So essentially, this model is grounding our logic system within the familiar territory of natural numbers.
Right, exactly.
So it's like we're restricting our libraries to only contain books that are labeled with natural numbers. Gotcha. And this seems like a pretty significant constraint.
It is.
Compared to the infinite sets we were dealing with. In sigma superscript 0 and compound.
Right.
Does this restriction affect what we can prove?
Absolutely. So Gassner points out that in N, AC, superscript n subscript n holds true for all n.
So this means that for any collection of n element sets, we can consistently choose one element from each set, even within this restricted model.
Exactly.
That's interesting.
Yeah.
So even with this constraint to natural numbers, we retain a certain degree of choice.
You do, yeah.
But what about TR1 and ZL1?
Okay.
How do they fare in N?
That's where things get even more intriguing. Gassner demonstrates through a pretty clever construction that's detailed on pages 12 and 13 that both TR1 and ZL1 actually hold in N.
Hold on. So in this model, where we're confined to this realm of natural numbers, both the law of trichotomy and Zorn's lemma, which were independent of HAC in compounds, actually hold true.
They do, yeah.
That's a pretty remarkable contrast.
It is, yeah.
To what we observed in compounds.
Right.
It seems like different models of second-order Henkin logic can lead to some pretty drastically different conclusions.
They can.
About the validity of these seemingly fundamental principles.
For sure.
This makes Gassner's open question about whether TR1 implies ZL1 in general even more fascinating.
It does.
How do you think?
Absolutely. These findings in N definitely add another layer of complexity to that question.
Okay.
So while TR1 and ZL1 coexist pretty harmoniously in this specific model, it doesn't necessarily mean that one implies the other in a broader context.
I see.
It's like observing a rare species thriving in a particular ecosystem, but not knowing whether it could survive elsewhere.
That's a perfect analogy.
Yeah.
And Gassner, true to her insightful approach, leaves us with further open questions and avenues for exploration. So on page 14, she touches upon this concept of dependent choice, or DC, and its relationship with the principles that we've been discussing. Can we briefly explain what dependent choice is and why it's relevant here?
So dependent choice essentially allows us to make a sequence of choices where each choice depends on the previous one. It's a slightly weaker principle than the full axiom of choice, but still powerful enough to prove many important results. And Gassner points out that the relationship between DC, TR1, and ZL1 in second-order Henkin logic is another area ripe for investigation.
So we're adding another thread to this already intricate tapestry of zogical connections. We have this interplay between choice axioms, the law of trichotomy, Zorn's lemma, and now dependent choice,
Exactly.
all subtly influencing each other
Yeah.
within these different models of
Yeah.
second-order Henkin logic.
It's fascinating stuff.
It is. It's a truly fascinating landscape.
It is.
And Gassner's paper serves as a brilliant guide
Right.
to this landscape,
Okay.
providing us this clear map
Yeah.
of what's known, what's conjectured, and what remains to be discovered.
Absolutely.
Well, dear listener,
Yeah.
our deep dive into the curious world of second-order Henkin logic has come to an end.
Whoa.
We journeyed through these different models,
Yeah.
explored the limits of familiar principles, and encountered some surprising results
We did.
that challenge our intuitions
Right.
about set theory.
For sure.
It's been an exploration filled with twists and turns.
Absolutely.
And these profound insights. And I hope this journey has inspired you to delve even further into the world of mathematical logic.
Right.
And maybe even embark on your own deep dive into the fascinating questions raised by Christine Gassner's work.
Absolutely.
So keep those mathematical minds engaged.
All right.
And never stop questioning the boundaries of what we know and what remains to be discovered.
Words to live by.
Welcome back to the Deep Dive. Today we're going deep, really deep into set theory.
Sounds fun.
Specifically, we're looking at Christine Gassner's paper, AC and the Independence of the Law of Trichotomy in Second-Order Henkin Logic.
Ah, yes, a classic.
So to set the stage, we're dealing with second-order predicate logic with Henkin interpretation.
HPL for short.
Right, HPL. Gassner uses this framework to analyze what are called the 1-1 Ackermann axioms of choice.
Denoted as HAC.
HAC, got it. So these axioms kind of focus on choice functions, but with a twist, am I right?
Exactly. They're more nuanced than, say, the full axiom of choice.
Okay, so how so?
Well, they guarantee choice functions exist, but only for specific families of sets.
Interesting.
And the paper, it really digs deep into proving these axioms are independent from other key principles.
Gotcha. Now, a crucial part of this proof is showing that 10 pounds in choice 11(1)H holds for any formula H in L2XD.
Right.
Can you unpack that a bit? What does that even mean, and why is it so important?
Sure. Basically, it means that in the model amounts, if for any x you can find a d that satisfies some formula h, then you can also find a choice function that will always pick a suitable d for each x.
So it's about consistently making choices within that model.
Exactly. It's a subtle but powerful statement.
So proving this for towns, that's like the foundation for showing all the 1-1 Ackermann axioms hold up in this model.
You got it.
But how does Gassner even go about proving that? The paper mentions something called permutation models.
Right, specifically 10 and compound.
Permutation models, what are those?
They're fascinating, really. They let us create variations of set theory by shuffling elements in a very specific way.
Shuffling, like a deck of cards.
Exactly. Gassner uses what's called the Fraenkel-Mostowski-Specker-Asser method to create these models.
Okay, so it's like creating these alternate mathematical universes where some rules hold and some don't.
Exactly, and that helps us see which axioms are truly independent of each other.
That's a cool way to think about it.
It's a powerful tool for exploring the logical foundations of set theory.
Now, inside these permutation models, there's this concept of finite stabilizers.
Right.
I have to admit, that one tripped me up a bit.
Haha, yeah, it can be a bit tricky. Think of it this way.
Okay.
You have a set and a permutation, which rearranges the elements of that set.
Okay.
A finite stabilizer for an element is the set of all permutations that don't change that specific element.
So going back to the card shuffling analogy, some cards might stay in the same position after you shuffle.
Exactly.
They're fixed under that permutation, and their stabilizer would include that permutation.
Perfect. You got it.
Nice.
Yeah.
So why are these finite stabilizers so important in these models?
Well, they're crucial for defining what we call predicates.
Predicates.
Yeah, essentially statements that can be true or false for elements in the model.
Okay, so I've got these permutation models. We've got finite stabilizers.
Right.
And then the paper throws in p-adequate partitions. What are those?
It's a way to break down the domain of our model, say, the set of natural numbers, into subsets based on their finite stabilizers.
So it's about strategically dividing things up.
You got it. It makes analyzing the choice functions within the model much easier.
And I remember the paper mentions they have to satisfy a specific support condition, right?
Exactly. That ensures each subset in the partition has a support. which is a finite set of elements
Right.
that determine its properties under the permutations.
I see.
It helps control how different parts of the domain behave when we apply those permutations. Crucial for the proof.
Wow, so we've got permutation models, finite stabilizers, and p-adequate partitions.
A lot, yeah.
Now, for the star of the show, the choice function. How does Gassner actually construct one in this setting?
Well, it's a pretty meticulous process. She creates a choice function on a family of sets denoted as AHI.
Lots of symbols there.
And this function selects a specific set from each family to satisfy that formula H we talked about earlier. It's complex, but the main idea is to start with choice functions on smaller, finite families,
Okay.
and then carefully extend them to cover the whole domain.
Got it. The paper even provides specific notations and formulas in Table 1 to help guide you through it.
It's like a recipe, right?
A very intricate mathematical recipe.
Exactly. And a key ingredient is a formula called swap Q plus 1.
Swap Q plus 1, what's that do?
It describes what happens when you swap elements in the model.
Okay.
It captures the consequences of permuting those individuals.
So it's like a rule book for how things change when you shuffle the elements around.
Precisely.
But why is that formula so important for the choice function?
Well, Gassner combines swap Q plus 1 with the choice function she built
Okay.
to make sure a specific predicate in the paper is definable within 2 pounds. This predicate is key to proving the 1-1 Ackermann axioms actually hold in the model.
So even after we shuffle things up, everything still works logically.
Exactly. It keeps the logic intact.
That's pretty clever. But doesn't the paper extend this to the compound model too?
You're right. It does. And that's where things get even more interesting.
Okay, so we'll have to save that for part 2 of our deep dive.
Sounds good.
Welcome back to the deep dive.
Yeah.
Ready to get back to those cum models.
Absolutely.
Last time, we were about to dive into how Gassner tackles them.
Right. And how it all ties to the law of trichotomy.
Okay, so remind me, what's special about com?
Well, you can think of it as like a union of copies of the basic Fraenkel model.
Multiple copies.
Yeah, it's like having multiple universes, each with its own set of permutations and those stabilizers.
Oh, so instead of just one deck of cards to shuffle, now we've got multiple decks.
Exactly. And we have to track how things change across these different copies.
That sounds tricky.
It is, but Gassner adapts the proof she used 4 pounds, taking those unique properties of com into account.
So how does the proof change? What does she do differently for com?
Remember that choice function we talked about for cones?
Yeah.
In compounds, we need a choice function that works across all copies of the Fraenkel model.
So like a master choice function for all the decks of cards.
Exactly. But it's not just a simple merge. She carefully aligns the choices made by each individual function.
So they don't contradict each other.
Precisely. And this involves some really clever use of those finite stabilizers and p-adequate partitions we talked about.
I can imagine the notation getting pretty intense here.
It can be a bit much, but the ideas are elegant. It's all about exploiting that structure of compound, how those copies relate to each other.
To make that coherent choice function.
Right, one that satisfies the properties we need across the entire model.
Okay, so once we've got this new choice function, do we still use that swap key plus 1 formula to keep things consistent when we permute stuff?
Yes, exactly. It plays a similar role in the compound proof, ensuring that permuting elements doesn't mess things up.
So it's like a safety net,
Yeah.
even with all these universes.
You got it. And by adapting the proof to compounds, Gassner shows that compounds equals choice 11-1H also holds.
Which strengthens the foundation for the whole paper, right?
Ex-
Okay, we've spent quite a bit of time talking about those choice functions in both models.
Yeah.
Now, how does all of this connect to the law of trichotomy?
Good question. Now that we've laid that groundwork with the 1-1 Ackermann axioms, we can finally explore the connection to Hartogs' version of the law of trichotomy, or TR.
Ah, right, TR. I was wondering when that would come back into play.
Now is the time.
So for those just joining us, can you remind us what TR is all about? Why is it so important?
Sure. It basically says that for any 2 sets, either one can be injected into the other.
Did.
Meaning you can find a 1-to-1 function from the smaller set into the larger one.
So we can always compare the sizes of 2 sets and figure out which one's smaller, even if they're infinite.
You got it.
That sounds pretty intuitive.
Right, it seems obvious. Like if you have 2 boxes, one must fit inside the other, or they're the same size.
Exactly.
But in set theory, things aren't always so simple.
Oh.
Especially with infinite sets, TR doesn't always hold up.
Wow, really? So there are universes where it's not true,
Exactly.
and we can explore those using these permutation models.
Precisely. And in fact, Gassner shows that TR fails in those compound models we talked about when phi is greater than or equal to 2.
No way. So even if you can consistently pick elements from sets, like the 1-1 Ackermann axioms say you can, you might not be able to compare the sizes of any two sets.
That's exactly right.
That's mind-blowing. So what are the implications of this? Why is this a big deal mathematically?
Well, it shows that TR isn't a logical consequence of those 1-1 Ackermann axioms in HPL.
So even if those choice axioms are true, TR doesn't automatically have to be true too.
Exactly. They're logically distinct in this framework.
So we can have universes where we can make choices, but the usual rules of comparing sets just go out the window.
That's one way to think about it.
Amazing.
And this independence result actually extends further. It also applies to choice, to X-ray, which includes all those 1-1 Ackermann axioms. So TR is independent of an even broader range of choice principles.
Wow, so this law of trichotomy really stands apart from all those axioms about choosing elements.
It does. It really highlights the power of permutation models in showing us these subtle distinctions in set theory.
And remember, we're doing all of this without needing the full power of ZFC, the usual axiomatic foundation for set theory.
Right. Which is even more impressive.
It's like we've discovered a whole new dimension where the familiar rules don't apply.
Exactly. That's the beauty of it.
So by showing TR is independent, Gassner really reveals just how complex and surprising things can get when we explore second-order Henkin logic.
She does. It challenges our assumptions about what's true in math.
Speaking of challenges, the paper also touches on the relationship between TR and the well-ordering principle.
Another fundamental concept.
Another one. Ugh, my brain is already full.
Don't worry, we'll break it down.
Okay, good. So how do they connect?
In traditional set theory, TR and the well-ordering principle are basically two sides of the same coin. One implies the other. But in HPL, things get interesting again. Gassner's work shows this equivalence breaks down.
So they can be independent in HPL.
You got it.
Okay, that's pretty wild.
Yeah.
But I feel like there's another layer here. Didn't we learn earlier that WL1 is also independent from choice 11-1H and TR1 in HPL?
We did. And that adds another piece to the puzzle.
Wow, this is getting complicated.
Yeah.
So even though we know all these things are equivalent in ZFC, they can be totally separate in HPL.
That's right.
It really shows how different things can be when we switch to that second-order Henkin logic framework.
Exactly. It's a testament to the depth and complexity of this area of math.
Speaking of depth, Gassner leaves us with a very interesting open question about TR and Zorn's lemma.
Yes. An intriguing cliffhanger.
But before we get to that, welcome back to the final part of our deep dive. We've been exploring this fascinating world of set theory with Christine Gassner's paper.
It's been quite a journey.
All those permutation models, choice functions.
Whoa, yeah.
Well, buckle up because now we're adding Zorn's lemma to the mix.
A classic.
So for our listeners who might need a refresher, what is Zorn's lemma all about? I vaguely remember something about chains and upper bounds.
Right. It states that if you have a partially ordered set, and every chain, which is just a totally ordered subset, has an upper bound within that set, then that set must contain at least one maximal element.
Okay, so if we have elements that are ordered in some way,
right,
and any increasing sequence has a ceiling within the set.
Yeah, like a maximum point.
Then there has to be a biggest element in the whole set.
Exactly. It's like a mountain range where every path you take eventually leads to a peak. And Zorn's lemma says there must be at least one peak that's higher than all the others.
That's a great analogy. So how does this powerful lemma connect to our friend, the law of trichotomy?
Well, in standard ZFC set theory, Zorn's lemma is actually equivalent to the axiom of choice.
Right.
Which in turn implies the law of trichotomy.
We're not in Kansas anymore, are we?
We are not. Remember, in second-order Henkin logic, those equivalences can break down.
Right. We spent all that time exploring how TR is independent of choice axioms in HPL.
Right.
Meaning you could have those choice functions, but the law of trichotomy might not hold up.
Exactly.
So where does Zorn's lemma fit into all of this?
Well, that's where things get really interesting, and where Gassner's paper leaves us with a big open question.
Ooh, a mystery. I love those.
So we know that ZL1, that's Zorn's lemma for predicates of arity 1, can be derived from AC11 in second-order logic with Henkin interpretation.
Okay, I'm following so far.
But both AC11 and TR1 are independent from ZL1 in HPL.
Wait, so even though they're connected in one framework, they can be totally separated in another?
Precisely.
Math is so weird.
It is. And to make things even more interesting, a while back, another mathematician named Asser asked a question. Does ZL1 imply TR1 in HPL?
So if Zorn's lemma holds for those specific predicates,
Yeah.
does the law of trichotomy also have to hold?
Exact.
Did you figure it out?
Well, the answer turned out to be no. There are models where ZL1 holds, but TR1 doesn't. So at least for those predicates, Zorn's lemma doesn't automatically mean the law of trichotomy is true.
Wow. So even though they're equivalent in ZFC, they can be totally independent in HPL. It really shows how much things change when we shift to this different logical framework.
It really does.
But what about the other way around?
You mean, does TR1 imply ZL1 in HPL?
Exactly.
Ah, well, that's the cliffhanger. That question, my friend, is still open. It's the one Gassner leaves us with at the end of her paper. She writes, does HAX2 TR1 AGL1?
Okay, break that down for us. What's all that cryptic notation about? What's she really asking?
She's asking whether, within a specific axiomatic system for HPL,
Okay.
the law of trichotomy for those predicates of arity 1 implies Zorn's lemma for those same predicates.
So is being able to compare set sizes using TR1 enough to guarantee you can always find those maximal elements using the L1?
Exactly. Can TR1 on its own do the job of ZL1? We just don't know yet.
So it's all about the logical power of TR1 in this framework. Fascinating. It's amazing how such seemingly simple questions can lead to such deep unanswered questions in math.
It is. It shows there's still so much we don't know.
Well, folks, that brings us to the end of our deep dive into Christine Gassner's incredible paper.
It's been quite a ride.
We explored those 1-1 Ackermann axioms, went deep into permutation models, and wrestled with the independence of the law of trichotomy. We even touched on the well-ordering principle and Zorn's lemma.
And we've seen how much the landscape changes when we move from ZFC to second-order Henkin logic.
It's like we've opened up a whole new dimension of mathematical inquiry. So keep those brains buzzing, keep exploring, and keep diving deep into the amazing world of math.